Isn't there a sign that says keep doors open?
Greetings and welcome, friends. Today we're continuing our look at logarithms, specifically referring to the properties of logarithms, Jacob. And the properties of logarithms, since logarithms are the inverse operation and inverse functions of exponential functions and the exponentiation operation, they are very similar to the properties of exponents in some ways. So let's start off with a little discovery, I might call this. Discovery. Discovery. Let's consider the following problem. Let's say I wanted to calculate log base 2 of 8 times 32. Okay? Log base 2 of 8 times 32. Now, it turns out I could actually rewrite both 8 and 32 as powers of 2. So this would be the same as log base 2 of 8 is the same as 2 to the third, and 32 is the same as 2 to the fifth. That's right, my friends. You guys are getting pretty sharp on those. Now let's see. Property of exponents. What would I do with those? Add them. Add those exponents. So log base 2 of 2 to the 8th. And now this was actually one of our quick little properties from yesterday, but we can also analyze it. Log base 2 of 2 to the 8th is asking the question, 2 to what power would give me 2 to the 8th? 8. The 8th power, right? So I would be done right there. Now, so that's one approach we could have, but let's alternate reality this problem, well, or maybe consider a different problem, slightly different anyway. What if I wanted to calculate what is log base 2 of 8 plus log base 2 of 32? So similarly, I'd be able to say, well, 2 to what power is 8? And that's the third power. And I'd say 2 to what power is 32? The fifth power. And I'd get 3 plus 5 equals 8. And you might realize these are the same. And yes, I understand there's math problems that have the same answers that have very little relation to one another, but in this case, these are very specifically related. There's a property between the log of a product and the sum of two logs, and that property is called the product property of logarithms. And let's see if you guys can determine what that property is. So let's see, the product property of logarithms. Logarithms. So if I have log base b of, say, m times n, all right, the log of a product, what do you think that will be the same as, based off of our experience here? And this guy and this guy. I like it. And that is, in fact, the property. All right? And the way my math professors used to say in college, he kind of had a nice little rhymey, not rhymey, but a nice little way of verbalizing this and some other properties. He'd say that the log of a product, for those of you who are maybe verbal learners, is the sum of two logs. All right? And that's the idea. So if I've got the log of two things being multiplied, I could rewrite that as the log of, or the sum of two logarithms where I'm taking the log of those two things. And yesterday I kind of mentioned the fact that logarithms have the power, the ability to change multiplication to addition. And this is the property that allows it that function, right? So I could change the multiplication of two numbers into the addition of two numbers. And this is where logarithms were very revolutionary in allowing mathematicians and scientists to be able to make their calculations much faster by hand back in the day. Now let's see. let's do an example applying this. I mean, there's a bunch of stuff we could do. For instance, up here, instead of doing all this work, I could have just said, oh, log base 2 of 8 times 32 is this, and then I've just gotten the answer like that. And I'll also be able to apply it in solving problems and not just evaluating. But let's say this. Let's say this following is true, and I believe it is. Let's say if log base 3 of 5 is approximately, all right, so squiggly equal sign, 1.4650. All right, that's an O, 0. And let's say log base 3 of 2 is approximately, actually, log base 3 of 2, would you expect that to be bigger than 1 or less than 1? That's asking the question, 3 to what power is 2? It's less than 1. Why do you say that, Hank? What are your thoughts? Or maybe I could ask this question, what number would go here if it was 1? 3 to the first is 3, right? So the fact that 2 is less than 3, I'd suspect that the exponent would be less than 3 as well. Or sorry, less than 1 as well. And this ends up being about, let me get rid of that box, 0.6309. So let's evaluate the following. All right, based on those facts. And this is kind of how people were able to, do some calculations in the past, and we're going to do them today. So if, for instance, I wanted to figure out what is log base 3 of 10. 3 to what power is 10? I have no idea. I don't know. But if I knew these two previous facts, I could actually discover this fact by rewriting log base 3 of 10. I could say, well, that's the same as log base 3 of, bless you, 2 times 5, right? 10 is 2 times 5. I think we agree on that. So log base 3 of 2 times 5, well, the log of a product is equal to the sum of 2 logs. Right? So we've got log base 3 of 2 plus log base 3 of 5. And log base 3 of 2 based off of our previous fact would be 0.6309 plus 1.4650. And I would just straight up add these. 0.6309 plus 1.4650. Bam. And I get 2.0959 as my answer. So what that's claiming is if I take 3 to this power, it should equal 10. All right. And let me verify that. 3 to the, oh dear, what did I just do? 3 to that power. Let's see if I can even, usually this comes on blurry. Ah, not bad. So here I added those two numbers, and I'm doing 3 to that power equals, and notice I get, for the intents of our rounding, we rounded to 4 decimals. If I round this to 4 decimals, that's 10, right? That's 10. So it does work out. Let's do one more like this. What if I wanted to figure out what is log base 3 of 25? How could I use this fact and this fact to rewrite 25? What's a... 5 and 5, right? 5 times 5 is 25. So this is the same as log base 3 of 5 times 5. And the log of a product is the same as the sum of 2 logs. Log base 3 of 5 plus log base 3 of 5. And what is log base 3 of 5? That was the 1.4650 plus 1.4650.
How do you know that? Oh, you just type it in the rectangle.
No, this was, they gave us 2 initial facts,
Okay.
is what they did.
On that first one, we put a 2 instead of a 6 down the bottom.
What did I do?
The first 1.4.
Oh, yep. There's that problem right there. Good save there, Evan, E-Man. Ooh, here we go. So let's see. 1.4650 plus 1.4650. Do 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 do. 2.93 double O. Is that what Hankford said there? I think he did. So this is claiming that 3 to this power is equal to 25. Now think about this. 3 to the second power is 9. 3 to the third power is 27. Right? So it would make sense that 3 to some number between 2 and 3 would equal 25. Let's just verify that. 3 to the second answer. Ah dear, what did I do? Second. Nope. What am I doing, guys? Here we are. Let's see. 3 to the second ants. There we are. Hit enter, and notice I get 25.0015. Pretty darn close based off of my decimal approximations. All right, so not too bad. So this in fact works out. Now, guys, consider this. We're going to do another discovery right here, but it's related to the problem we just did. We're going to discover another property. It's like an adventure. Here we go. Let's go Bear Grylls on these properties of logarithms. Let's see. Okay, here we are. So, discovery. Log base 3 of 25, would you agree, is the same as log base 3 of 5 squared? Agreed?
Yeah.
And this piece right here also equal to log base 3 of 25, and therefore also equal to this. Would you agree that I could rewrite this piece here as 2 times log base 3 of 5? Right? If I viewed these as kind of like terms, I mean, even when you see their decimal values, you can see, oh, that's just 2 of those. Right? I was almost tempted when I plugged that in the calculator, just write 2 times 1.4650. So do you guys agree that this is 2 times that? Agreed? Agreed? So what is a relationship between this line and this line? This one doesn't have the square. Yeah, it kind of looks like we move this to the front. I think Evan's correct. And to prove this concept, let's consider, what if I wanted to calculate log base 3 of 125? Well, that would have been the same as log base 3 of 5 cubed. And in fact, if I did 5 times 5 times 5, thinking about it, kind of this approach, right? 5 times 5 times 5, it would have just had one more log base 3 of 5 here, right? And what is 3 of those added together? Well, that's just 3 times one of them, right? Agreed, agreed? So I could rewrite this as just 3 times log base 3 of 5. And the relationship between this guy and this guy looks like this guy was just moved out front as a product. Huh. Yeah. Looks like indeed. And it turns out that we have just discovered the power property of logarithms. Power property of logarithms. Which says if I have log base b of m to the p, Evan, what do you think I could do with this power? I could move it out front and rewrite this as p times log base b of m. All right. And one of the subtleties of this property, just to avoid misinterpretation, log base b of m to the p means, let's see, log base b of m to the p, you could view it like that, I guess. All right. It does not mean log base b of m all to the p. All right, so this one's a no. All right, a no on that. So this is a correct interpretation of this. The whole thing all to the pth power, does not mean the same thing. Okay, just to verify. Good. So let's see. We'll end up incorporating that property a little bit later, but let's do one more discovery to discover our third property of logarithms today, since we're on a roll. On a roll, friends. Let's say I wanted to do some work with log base 3 of 5 divided by 2. All right, 5 divided by 2. Now, I don't have a log of a quotient property just yet, but let's tinker around with this. Would you agree that this is the same as log base 3 of 5 times 2 to the negative first? Right? Dividing by 2 is the same as multiplying by 2 to the negative first. Agreed. And using our log of a product property, the log of a product is equal to the sum of 2 logs. I'm going to keep saying it. I think they say that memorization can occur after around, 16 repetitions of the concept? Something like that on average. I don't remember. So the log of a product is the sum of 2 logs. So log base 3 of 5 times 2 to the first, negative first, is going to be log base 3 of 5 plus log base 3 of 2 to the negative first. But wait, there's more. What could I do with this exponent? Move it out front. And instead of plus log base 3 of 2, I can change this to minus, because just multiplying this by negative 1 is going to do the same as that. So log base 3 of 5 minus log base 3 of 2. So could anyone generalize a shortcut property to go from the log of a quotient? How would I? Could you verbalize what happened there?
Is it always going to stay or like be minus?
Yeah. So how could you guys put that into words for me? Someone give that a try. The log of a quotient is the difference of 2 logs. Let's write this down. Make it proper. So here's our quotient property of logarithms. I'm just going to say logs. We all know what I mean. And so the quotient property of logarithms says that if I have log base b of m divided by n, the log of a quotient is equal to the difference of 2 logs. Aha. Right? Not too shabby. Good stuff. So the symmetry that I was talking about in terms of the properties of exponents, I think the quotient property and the product property are very similar to exponents. I want to scroll over. I'll come back to that in a second if you're still writing it down. Notice this one, the log of a product is equal to the sum of 2 logs. I view this the same as a to the m times a to the n equals a to the m plus n. Right? That was our property of exponents. Right? The product of 2 powers is equal to the sum of their exponents as a single power. Right? Same sort of idea. Multiplication became addition. Bam. Right? So that's kind of that similarity. Over here, division, right, became subtraction. And a to the m over a to the n was equal to what? A to the m minus n, right? So you can see kind of the similarity. Division became subtraction. Division became subtraction. So if you're familiar with those properties of exponents, the logic is symmetric. It's not identical. It's symmetric. It's similar, I might say. So let's do some examples with this. Combine some of our properties. So one of the types of problems they'll have you do is say write as a single logarithm. Logarithm, right? And they'll have a problem like this where they'll have 3 times log base 2 of x, let's say, minus, let's actually fancy this up. Let's make this, 1/2 times log base 2 of, let's say, 9. How about? I like it. So, if I wanted to write this all as a single logarithm, I'm not going to deal with the subtraction yet. I'm going to use our power property, right? Our power property of logarithms said that if I have a log to a power, right, that I could write that power or exponent out front. It turns out going backwards, I could write these coefficients up top, all right? So that's going to be my first move in writing this as a single logarithm. And this skill of being able to write it as a single logarithm is going to be helpful in the next kind of problem we do. So let's see. So that's going to be the same as log base 2 of x cubed. This will be the same as minus log base 2 of 9 to the half power, right? And now what's the difference of 2 logs the same as? I could write that as a single logarithm of what? Subtraction is similar to, becomes the single log of division, right? So, so I could write this as this guy divided by this guy. So x cubed divided by, but wait a minute, there's more. 9 to the 1/2 power, what's a half power the same as?
Square rooting it.
Square rooting it. I like it, yeah. Represent Jacob right there, bam.
Yep, Jacob Hicks.
And the square root of 9 is 3. Right, so I was able to write this as a single logarithm. The parentheses, I don't know, maybe they're helpful. I think it can be a little bit to do that. And let's see, one last problem. Let's see how crazy we can get here, putting these skills to the test now that I can manipulate logarithms like crazy with all these properties I know. Let's do a solve problem. And this is going to look crazy. What if I want to solve the following? 2 times log base 3 of 6 minus 1/4 times log base 3 of 16 equals log base 3 of x. So, my general strategy for this. Now, the only way we've been able to solve problems that had logarithms in them so far was to get a single log on each side and then drop them, right? Because we know that if I have 2 logs that are equal and their bases are the same, then their ofs were equal as well. So if I could get a single logarithm on this whole side equal to a single logarithm on that side, that would be nice. So write as a single log. Is going to be my first objective. I mean, the other strategy we had for solving logarithmic equations was if there was just one logarithm in the entire equation, was to kind of rewrite that in exponential form if that was helpful to us and, you know, solve from there. But so let's see, if I want to write this left-hand side as a single logarithm, first thing I'm going to do is deal with this 2 and this quarter, and I'll move those up top. Up top, friend. High five. Here we go. So this is going to be the same as log base 3 of 6 squared minus log base 3 of 16 to the 1/4 power, which is the same as 2. Wow, jumping way ahead there. I agree. Same as a 4th root of 16, which is going to become 2. All right. And log base 3 of x just hanging out here. And then let's see, the difference of 2 logs is the log of a quotient. So 6 squared is going to be 36, divided by 4th root of 16 is 2. Right? And now I've got a log equal to a log. Their bases are the same. Therefore, their ofs must be equal, right? The two things in parentheses here must be the same. So I'm going to get x equals 36 divided by 2, or x equals 18. Interessante. However, we still have to take into consideration, when I plug this x back in, will any of my log ofs be negative? And in this case, if I was to check here, no, we're cool with that. Right, log base 3 of 18. 18 is positive, we're fine. So, so this would be the answer. So not too shabby. Quite a few properties we were able to discover today. Log of a product is equal to the sum of two logs. Log of a quotient is the difference of two logs. And a log of a power, you can take the exponent and rewrite it as multiplication. So all sorts of cool stuff that logs can do that you've never been able to do before. Adios, amigos.